introduce again Jamie Mingo for his third part in the series, great series he gave. So the title is, as you can see, free random variables, moment-cumulant generating function. Jamie, please.
Thanks. Okay, so I've been rewriting my slides as the meeting's going on, just to try and sort of make it more precisely targeted to what I think people are interested in. So I changed everything last night, and hope I didn't introduce a bunch of typos, or anyway, we'll see. So let me just go back a little bit. So remember we had the moment generating function, which said you can write a moment as a sum of cumulants. And that led to this equation where you parameterize the block containing a single point, which we took to be 1. And then this gave this way of writing a moment as a sum of where you take a cumulant and then some other moments. And then that turned into giving this relation, which gave the, this is the moment generating function, and that's the cumulant generating function. Then you can turn that into that relation that Voiculescu had, which is the crucial relation in free probability. And now what I want to do today is do the same thing for higher order, well, second order.
For only one.
That's just for, this is just for the first order moments and cumulants. So non-crossing partitions, which you could write on the line or on a circle, but just one circle. Okay, so just repeat what I said before. So that's the R transform. So there's this shifting. So historically, I guess that's why we do it. The Cauchy transform G, the exponent on the Z is one more than the subscript on the moment. And I see I had an alpha instead of an M there, but sorry. At some point I was calling them alpha just so that I didn't have M sub M. But anyway, I decided that the M sub M is okay. I could live with that. Right, and then the other form of the moment is just this thing here. In second order, remember we had these second order moments. So you assumed that you had some random matrices, and you took the mth power of the matrix, you took its unnormalized trace, that gave you some random variable. And then you took the nth power of the matrix, you took its trace, and that gave you another random variable. Now you got two random variables, and you look at their covariance. And then the size of the matrix go to infinity, and we assume that that converges. And it does in lots of examples, but here we just assume that there's some limiting moment, which we call M sub M comma M. Question in the chat? Okay. Yes, and then we had the second order cumulants, which were given by the second order moment cumulant relation, but now we used an annulus instead of a disk. So we looked at non-crossing partitions on an annulus, and there were two kinds. I'll put it up on the next slide. Excuse me, I'll put it up on the next slide, but there were two kinds of.
Have you shifted this definition of R?
I did, that was a typo before. So somebody asked me and I said no, but they were right. I forget who asked me that. Yeah, maybe.
Do you have to shift it up to Zn plus 1 and Wn plus 1? So you should now shift it down. I thought you have to shift it.
Okay, I don't usually write it like that. So I think it's in here, but I think that's right. But anyway. Yeah. Okay. Thanks. Yeah. Okay, so yeah, I got it wrong before. I just wasn't. So I have this C, which you don't shift it, and the R, which you do shift, and I was just confusing the two. Okay. Yeah, I started to think about it. You see how here there's a shift one way, and there's you got to shift the other way. In the other formula, they did no shifting either way, and then it worked out just better. It was better. So exactly why, I don't know. It's just okay. And so today what I want to talk about is this, this expression right here. So that this combinatorial relation between moments and cumulants at the second order, we were able to show that it gave you this formula here. Actually, it took us a while to even, we had a gigantic formula, and it just looked hopeless because it was just sums and derivatives and products and there's an equal sign up over here, and a plus sign, So there's two parts. There's the second order Cauchy transform. There's the second order R transform evaluated at the Cauchy transform on Z, and then the one on W, and then you have derivatives on the outside. And then there's this other thing with this second order mixed partial of a log of a difference quotient. This expression is somewhat interesting in the sense that I can compose G with any fractional linear transformation, and that expression is invariant under Möbius transformations. So in the first version of the paper, we had just a G. And now you say, why did I bother doing this? Well, if you write a 1 over G, this power series expansion starts with a Z minus W. And then it cancels with this Z minus W, and then it's 1 plus something. And in formal power series, you have to have a 1 plus something to take a logarithm. And before, the thing we had wasn't really acceptable as a formal power series, but you could just do the differentiation and write this instead. And so if anybody was going to call us on it, we just said, no, just differentiate. But if you put the 1 over G, then actually as a formal power series, it's a legitimate expression. Since you're differentiating, it doesn't really matter that much. But then a few years ago, Gaetan or Elba, I can't remember, maybe both together, showed me that this equation, and this is part of their work, could be written in a really compact way. That you let zeta be G of Z and omega be G of W. And it just says that these two differential forms are the same, one with a G and one with an R. So I don't know how to use that for anything, but it's an astonishingly compact statement compared to all these other things that we found. Well, no, you just formally, I don't know. I mean, you just formally multiply symbols. And that's what you get. What it means, I don't know. Right. No, but I'm just thinking, I mean, I think this, I'm hoping this is connecting to what Alex was talking about, XY symmetry or something. One of these is X and the other is Y, right? Isn't that it? Yeah.
It's actually, if you have a row at a certain point, either small y, capital, I mean, I choose either small y or capital Y.
Yeah.
There's actually this difference between, right, zeta equal to G of Z or the inverse.
Yeah.
It's exactly some of this thing here. So.
Yeah. Okay. So there's a certain deeper meaning to this than just some formal symbols. Yeah.
This is also the cylinder.
Yeah.
Okay.
The exact equation.
Okay. Okay, great.
This equation does not appear actually in this book. I mean, for omega 02, the Bergman curve.
Yeah.
And then you say that for the spectral curve XY, you have the Bergman kernel. And then you say that for the spectral curve YX, if you interchange, you have also the Bergman kernel. They are equal. And then this will lead to this equation.
Okay. So now I'm going to show you the hard way of proving this. Yeah, so I just, before I dig into it, I just sort of remind everybody of what the notation is. So we use this thing to be the non-crossing annular permutations. So it's just, you put here 1 to 12 clockwise around the outer circle and 13 to 18 counterclockwise on the inner circle. And you look at partitions so that when you draw the cycles, and you have to go around these, and I didn't put arrows on them, but go around in a clockwise direction, the cycles don't cross. So these are the partitions for which there is a way of drawing it such that the cycle blocks don't cross. Then there was another component to this thing, which I called PSNCMN primed. It's a terrible notation, but I still haven't been able to think of something better. And that means you take non-crossing partitions on one circle and non-crossing partitions on another circle, and you choose one cycle in each. So you mark in each color, in this case, one cycle on each side. And yeah, so here I forgot to say, you have to have that they connect, that the pies have to connect the two. There has to be at least one cycle that goes between the two circles. That's part of the definition. Okay. And if I take the union of those two sets, I call that PSNCMM. These are the non-crossing partitioned permutations on an MN annulus. And that's the index set for going between moments and cumulants. In the first order case, it's just non-crossing partitions of the disk. And the second order case, it's non-crossing partition permutations of an annulus. And how did we decide on this? We wanted to make this rule about fluctuation, that cumulants would linearize second order freeness of fluctuation moments of random matrices. So the reason for doing this was to make the R transform of the sum equal to the sum of the R transforms. And this is what you have to do if you want to get that. So that's what the driving force for this, for all of this stuff. So that's what we found. Okay. So let's look at one example. So this is, there's going to be two steps to getting that equation. So here's the first step. And this same method here, we also used a little bit in a paper that with Octavio, though he didn't get a chance to talk about it because maybe it was too much into the detail, but I'll try and expose this idea here. So it seems like a useful idea. And I haven't really tried hard, but it might go up to more than 2 circles. We'll see. So here's the 2-2 moment written as a sum of cumulants. You add up these coefficients, you see it adds up to 18. No, that's not right. If you add up the ones that don't have any second order things, it should add up to 18. Right, where did look? There's 4 plus 8, that's 14 plus 4 is 18. Yeah. And then over here, there's 4 plus 4 plus 1. So there's 9 on the second order, so on the partitioned ones, and 8 on the ones where there's a connecting cycle. So let's just say what the 18 are. So there's going to be 4 of them that have one cycle of length 4. So there's 4 ways of making a cycle of length 4. You just have to decide when you leave the outer circle, you could either leave from the upper point or the lower point. And when you go over, you could go over to either the 2 points on the inner circle. So there's going to be 4 ways of doing it. And then there's only one way to finish it off. Now, what about where you have?
So in this first example, to connect from the outer circle the 2 points, and from the inner circle the 2 points from the other side of the inner circle. So
yeah, let me draw them on the board. I think that'll clarify. So here's, now you gotta, it's oriented, so you gotta put arrows on it. So You see. That's two of them. And then, yeah, then the mirror images.
Yeah, I mean, okay.
Yeah. What did Jonathan say? The closer you are to the board, the harder this is to do. Let me see. So so here I did 1 to 2, and there I did 1 to 3. So I have to do 1 to 4. Okay. So there's 4 of them.
But I mean, you have now in the first diagram one of these connections on the right-hand side of the inner circle.
Yeah.
On the first one, then you have one of this connection.
Well, I mean, you number the points. So this is, so I didn't put numbers in, but the numbers are the same. So this is 1, 2, 3, and 4. So
you
it,
can connect 3 and 4 also from the right-hand side. It's the same position. I mean, this is the good. This is the same position. Okay.
yeah. So the thing is, the crucial thing is that you count permutations. So this is 1 to 3 to 4 to 2. And what about this guy? Well, this is 1 to 2 to 3 to 4. Okay, so there's 3 factorials. There's 6, yeah. There's 6 cycles of length 4 in the permutation group, but 2 of them don't satisfy this condition. So they only look at these 4. And yeah, Andrew isn't here, but I can still remember sitting in a cafe in Waterloo having a discussion about whether, when we were doing this, we counted partitions or permutations. And we couldn't really decide because we were just making this up, but we did a calculation with the Wishart matrix. And it turned out to get the right answer, you had to count permutations. So that settled it. That order, the phenomenon that we were trying to capture required you to take into account the order, but in a special way. And of course, at this point, we were topological babies, and had absolutely no idea what to look at. And we looked at books, and nobody ever seemed to ever talk about this question. And topologists seemed to say, I don't know, it's not very interesting. But anyway, eventually we sniffed it out. And it turns out you got to use permutations. Yeah, now the same thing here, there's going to be one way, there's 4 ways of putting that singleton. You can put it at the top, here, here, or there. So that's 4 ways. And for each other way, there's going to be 2 ways of orienting the cycle. Daniel.
So you're not about to find boundary circle, like to do one.
The idea is that the way to think of it is that you have to enclose from a topological point of view. You have to enclose a region, and the boundaries got to go around in the way that in complex analysis we would call the opposite, and wrong orientation. But you have to enclose a region. And now it looks pretty scary here because you say, oh, okay, we're getting into some messy topology, but actually everything happens by counting cycles. When you actually prove something, you can't really prove anything with these pictures. At least you can't do it rigorously as far as I can tell, because there's just no way. You have to invent a whole language for manipulating a picture. So you stretch it and you do some homotopy theory and this and that, and you cut it here and you glue it there. And but if you do it in the symmetric group, it's just algebra. Now, you can't write down the algebra until you look at the picture. So the pictures are very important because otherwise you haven't a clue what to do. You just try random products that would never work out. But I don't think you can really prove anything with these pictures. Okay, And yeah, so here with something of cycles of length 2, you could either, this guy could go to here or it could go to there, and that's it. And finally, if you have 2 singletons and 1 pair, there's, yeah, so you can't put 2 singletons on the same circle because that would mean it's not connected to the other circle. So there's actually just 4. Okay, because you can put this guy on the top of the bottom and with that guy on the top of the bottom, and then the rest is forced. So yeah, if you just sum over these ones where the pi connects the 2 things, you get these 18 terms. Okay. So now what about the next thing? Let's look at P. Oh, that should be PS, sorry, not P. That should be the non-crossing partition permutations on a 2-2 annulus where it's disconnected. There's no cycle. So you can have that connects the 2 circles, but you mark them. So I've marked them in pink here. So here's the case where each circle has just 1 block of size 2, and you have to choose. There's only one way to do that. There's only 1 cycle here, so you choose that. There's 1 there, you choose that. Then you can have 1 circle has size 2, and the other circle has 2 singletons. So you use a choice of whether you put the cycle of size 2 on the in circle or the out circle, and then there's a choice of which thing you do. So there's going to be 4 of those.
But 2, both cycles are on the right-hand side, right?
It doesn't, yeah. So it has no idea, yeah. You don't care because it's all in the permutation group. Yeah, so you can draw it, and that's going to be important actually, that we have that freedom to draw it however we want. And then finally, you have all singletons, right? So here, yeah, so look, you have the marked blocks, each have 1 element, so you get a kappa 1, 1. Then there's a singleton here and a singleton here, so each give you a kappa 1. And then again, there's 4 ways of doing that. Now, here's the new twist. Let's look at the non-crossing annular permutations where all blocks are through, or all cycles are through cycles. Well, there's those 4 guys here. You already saw those. And then there's the other ones where you just have 2 cycles each of length 2. And all the other ones had a cycle that didn't connect to the other circle. I couldn't get these all on 1 slide, so I may have to do a little zigzagging. Okay. So here's the idea. Yeah, okay, so we're going to try and sum over this set here. And it's very hard to parameterize it. So remember that thing I did before on Monday? You choose the block containing 1, you describe that block, and then you look at the gaps. So I want to do the same thing now, but on 2 circles. But it's pretty hard to describe a general configuration here. But we found a way, which I hope will extend to 3 or more circles, but I haven't really pushed it. And it goes like this. I'm going to introduce some new dummy cumulants.
SNC all does not have singletons.
It can't, that's not the only condition, but what you said is correct. Every block, every cycle has to go between 2 circles.
Okay, this is the condition. Okay.
Yeah, that's the condition. And that means you can't have singletons. Yeah. Okay. So I'm going to introduce some phony cumulants. So the first order ones, okay, they're just the same. But the second ones are different. I sum the real cumulants, but only over the non-crossing partitions where all cycles go through. Okay. And so, yeah, here I just computed some of them. Kappa 2 tilde. We saw there's 4. I mean, you just go back. Remember, there's 4 of those. And they all have 1 block of size, where you get that. And then there was 2 of the other ones. And then you can do these other guys. Now, here's the, I wish I didn't come up with this idea. I wish I would claim that this was in the paper, but there was 4 co-authors. And that wasn't my idea, but I would like to claim this. It says when you sum these things, it's the same as summing the phony cumulants over the partitioned ones. Summing over these annular things, which are connected, is the same as summing the phony ones over the disconnected ones. And yeah, if you just do this, you plug in these things, you get exactly those formulas. I don't think I didn't put it on here. Sorry, but if you go back and plug these in, you get exactly this this thing down here. Sorry. So yeah, this is one of these things that maybe you just see, but there's actually a proof. It goes like this. Here's something at SNC. Some cycles go all the way through, some don't. I take the cycles that go all the way through, and I take the part that lies on one circle, and I make that just as one cycle lying on one circle. And I take the part of these things that goes on the other circle. So look, on the inner circle, there's 4 points. And so I make that a block. I make this disconnected by making that a block on the inside circle. And I take these 6 points and I make them a block on the outer circle. And then I do this thing I did yesterday where I make this green thing. Well, I turn that, there's the block of size 4, there's the block of size 6, and I put them like this and I make an annulus. And then I draw these crossing guys inside the annulus. And these ones this will be an annular one where everything crosses, because I only worked on the crossing cycles. So remember I said you can't prove anything with pictures? Well, okay, maybe you can. And yeah, so on the next slide, yes, I just drew the corresponding, there's the block of size 6 and the block of size 4, and the other ones I didn't change. So what you do is you take all of the things in SNC and you group them according to that construction. Every one of these things will give you one of those. So this is a big sum, and then you write it as a double sum by conditioning on this. And then what's left inside is that. That's the proof. It's just conditioning. You take a sum over a big set, and then you introduce a parameter, and then you sum over the parameter, and then inside for each fixed parameter, you have another sum. So that's the proof. But what do you get out of this? Okay, so here's something that's true for any power series. This has got nothing to do with cumulants. This is something that's just about a formal power series. So I start with some formal power series, and I do this. I make a power series in 2 variables by taking alpha I plus j times z to the I w to the j. Okay, and this is a little calculation, but okay, it's just something you can do with formal power series by taking some partial derivatives, actually. You formally take partial derivatives and then integrate backwards. Just like when you want to summation n times z to the n, you say that looks like a derivative, that n, and then you can just solve it backwards. So same kind of calculation.
This reminds me of the recursive relation in the conservation model. It's the same form. Somehow, how you relate the 2-point function with the 1-point function with the quotient. I mean, I don't know if there's a relation.
Yeah,
It
okay,
looks
yeah.
exactly the same. It
Yeah.
comes from this water entity, for instance.
Yeah, okay, yeah, anyway, this is just that's not, yeah, we just said, okay, how do you sum this? And we sat down with a piece of paper and said, okay, anyway.
So you can do it also for a third order power series where you have f of z, w, y, and so on.
No, you know what? We never even thought of trying. I never even thought of trying. Somehow I was so scared that we got out alive of this paper that you just said, never going back there again. But okay. But now when you go back, actually, it's not, now you see these other connections. It's not so scary. Okay. So that's that set of non-crossing annular permutations, like over there, where all the cycles connect both circles. Okay, and I'm gonna if I take any power series, and I just do this. Remember what is that alpha pi? If I have a cycle of length 3, that means I put in an alpha 3. That's the whole thing. So for each pi, you say what are the size of the cycles? Say that it's 1, 7, and 7, then it would be alpha 1, alpha 7, alpha 7. And you sum that. And I call that alpha tilde. And you say, what's the formal power series for that? Okay, so we call that F tilde. And so one of the theorems, that's what step 1 is that this formal power series is given by this, where this hat is that hat up there. Okay, and let me just jump back for a second, then I'll come back to this slide. Remember, to prove this one, the key thing was to do this. That was that parameterization. So now I'm just going to show you the parameterization. When the parameterization of alpha tilde in terms of alpha is this. And the point is that these things are much easier to describe where all cycles are through cycles. Okay, that's the step. And there's a picture on the next slide that just shows you how to do the parameterization. So R will be the number of cycles in pi. Now for each cycle, you count how many points are on each circle. In cycle 1, that will be I1, sorry, on the outer circle, and J1 will be the number of points on the inner circle. So they have to add up to m, because it's got to be a partition of m, a permutation of m things on one circle and n things on the other circle. And then in the next slide, I'll explain this. So
is it obvious that it's symmetric between m and n, the alpha tilde?
It's not from this formula, because I just chose something on one circle to do it. Yeah. So yeah, then you choose a marked point on one circle. And it's going to, and the block number 1 is the block containing that marked point, and then we number them clockwise. So there's I1 points on the outer circle that marked point could be in. Then, when this, so say here, this would be the marked point. And then you say, where does that outer thing cross over to the inner side? Well, there's n ways, there's 2 in this case, there's n ways it could go over to the other side. And then I have I1 points on one side and J1 points on the other side, so the contribution is just alpha I1 plus J1. And when you have all cycles crossing, you get what you might call a spoke diagram. Ta-da. That, look, you have an interval on the outer circle, another interval, and then you have intervals on the inner circle, and you're just connecting them. Okay, so you can completely describe this thing with just some indices. And then how to go from here to here? Well, you just sum and you write this thing, and n is equal to the sum of these j's, and you stick them with this thing, and you interpret that as a derivative. So on just so manipulations, this usual manipulations with formal power series, it's a calculation and you got to do it a couple of times and maybe you simplify it and you can find ways of writing it. Yeah, and of course you got to here and then we got to something and then we had to do this thing, but so I showed you that first. Anyway, that's step one. So the thing is that if you start, so the alphas are going to be cumulants, but I just wrote it as alphas because it's general. But when you do this thing over all through cycles, you can write down a formula. Okay. Step two. I think this is the last slide. Okay, I'll go slowly. Okay, because this is a big step. Okay, so here we have some cumulant sequences. Yeah, first order, second order. There's my moment generating function. That's, and then now I do this thing. I let kappa bar be the regular kappa plus this kappa tilde, where this is the phony one. Remember I talked about the where you just sum over these things. Okay, and remember we had that theorem, that little lemma, that summing the real ones over these guys is the same as summing the phony ones over the ones where there's two pieces. And these guys are easy to parameterize. So that's the step here, is that I can parameterize these things because I can easily do the ones on one circle and I can do the ones on the other circle and I can just stick them together. Okay, now that's so I think there's a way of proving this thing that that says that's one of these guys where you take either a real one, second order one, or one of these phony ones. And so this is a sum of two things. And you see there's let me just say what these things are. So you have to decide whether your mixed point, your marked point on each circle is inside one of those specially marked blocks. So there's 4 cases. Okay, and so this is both out in one, but not the other, in the other, but not the first one, and in both. You have to say where it comes. So there's going to be 4 terms, and that's exactly gives these four things here. Those 4 terms each come out from putting one of these guys in this sum, and the rest of it is just again the standard manipulation of composing one power series with another. So that's really all there is to it. And then you use that, we have this sum over here. So we get h of this, and then you get this formula here. And then this is the thing we wanted to solve for. So I don't got to go through the rest of the algebra. It's just, I don't know of any easy way of doing it. You just grind it out and you get back to this formula way back here. But actually, there's a long way to manipulate these things. And as I said, didn't really know that there was going to be a nice answer. And every now and then one of us came up with a simplification just by playing with it. But this is the champion for simplification. So that's all I wanted to say. I just realized I was supposed to take my mask off. I forgot.
Any questions or
Yeah.
comments? Can I ask something? If you go to the last slide, so you have there this kappa bar, this kappa mn, plus this kappa tilde.
Yes,
In this kappa tilde, they are just first order contribution of kappas, right?
that's right.
And the whole second order contributions are in this kappa mn.
Right.
But then you get this products I mean, at the end of this formula, you get product of second order times first order.
Yeah, so you see in here, you get everything because this is this contains both things at once. That's the point of that.
Yeah.
And but the whole point is that if you just summed over this thing, it's not too hard to write something down because of this parameterization here. But this would only give half of the terms. And the idea was to push the tricky part about the connected ones into the disconnected case by doing this kappa tilde trick.
Questions or comments? Yes.
Well, I mean, in some sense, yeah, I mean, Gaetan and Elba and company have actually solved this problem completely, although I haven't read their proof or even tried to read it. I mean, there's a lot of, for me, it would be a lot of work because I noticed that even when they multiply permutations, they use a different convention. I have to take their paper and put it in the mirror in order to read. But as far as I understand it, and maybe, yeah, I don't know if there is anybody from that group on the Zoom. You can ask them a question. I mean, it seems to me that you could take something like this and make it go to 3 or 4 circles. Use this idea of doing, yeah, the ones that are easiest to understand are these guys, because you're just down on 1 circle, and that's the thing that is so easy to do. And then it's easy to describe those, so you can write down explicit parameterizations. These ones are really complicated to try and parameterize. And so, but the fact is you can reduce it by this phony cumulant trick. But this idea of sticking something inside, that should work on anything. Whether it can be made to work, I don't know, but that seems to me something that's worth trying. In our paper, we just state the lemma and say it's more or less clear, but I mean, I think this picture makes it a little clearer how to do it, but it's just the conditioning. You have a big sum, and you take each element and you tag it by parameterizing a certain way by one of these guys. And that's exactly what Octavio and I did with these even second order even things. We had to take the sum and decompose it according to some other partitioned guy. And that was a necessary step. And that's really why, remember when he gave his formula, there were 2 terms. There was this funny other term. And that was exactly one of those was one of these phony cumulants that was needed to make the thing work. So yeah, as to what could be next, there's lots of things where this side of the calculation could be pushed to 3rd order. And on Friday, Daniel is going to tell us about some explicit calculations with 3rd order cumulants. But as far as I know, he's the first person to go there.
No dysfunctional relation in
Yep.
3rd order. Taken from
Yep.
the paper. You guess this relation between the kappas, kappa tilde, kappa bars in 3rd order?
Maybe. I mean, I would think the thing when you go to 3rd order, remember Elba had these graphs, right? There's going to be 4 graphs. So there's actually a bunch of terms. But I mean, it seems that it's only the 2nd order one that has this complicated thing. I really find that kind of mysterious in their work, that because from Daniel's work, the 3rd order gets way more complicated than the 2nd. So maybe they have some secret technology there that makes it simple. I don't know, but usually the more circles, like just imagine someone gives you a permutation with and you offset on points on 17 circles. And you've got to decide whether you can draw that in a non-crossing way. Turns out there's a computer algorithm that does it, but if you try to do it by hand, it would really take a long time. If you just did it by trial and error, it would be like, when you do a Sudoku puzzle, you put a 2 in there and then you discover a contradiction 18 moves later, and you go and erase everything back to that, and then you put a 3 in there, and you see if you can get a contradiction, and so on. Yeah, that would be the sort of the standard thing. That sounds a little bit like when Andrew was talking yesterday about the problem of finding the shortest path. That looks like, but the strange thing is the problem about deciding whether something is planar is actually completely machine doable, because you just count cycles. And so whether that problem that Andrew had could be turned into something that's machine doable, I don't know. I mean, if you just come at it one way, it looks like a smooth vertical wall. But who knows? Okay. Well, I think I can show it, right? It's from Elba, yes. I think it can work, but we never finished the computations because it seemed too difficult to generalize. Now that we have an ansatz, that's definitely worth trying to match. Anyway, the fact that people seem to care encourages us to try. Well, I have the same thing, yeah. That when we did this paper, everybody just said, wow, that's such a monster. How could you ever use that? And now there's a connection to something.
Simpler question is the relation.
Yeah. Let me see which.
I mean,
Okay, I don't know. I mean, that's at the moment. So, whoops, something went wrong. Okay. Okay. Yeah. Yeah. So, yeah, here's something. So, in a lot of ensembles, this guy is 0. R is 0. Sorry. Second order cumulants vanish. Yeah, that's right. A lot of Gaussian things, the second order cumulants will all be 0. And so you just have this thing equals this thing. And in univalent function theory, this is a very interesting thing, this derivative, because when you let z goes to w, you get the Schwarzian derivative. And so, yeah, and a lot of examples in the statistics literature and so on, you just get this. I mean, what does it mean when this is 0? It means you don't have to do any second order cumulants, which means you can do everything with connected diagrams. So, for example, for the GUE, I think this goes back to Harur-Zagier or beyond, or that. You know, when you compute those things, you can do everything with pairings, right? It's just annular, it's non-crossing pairings for all orders. It's not, I mean, the highest leading order terms are all non-crossing pairings on a surface of genus 0. So you don't need any second order things. Therefore, that's 0. And therefore, these things are just given by a much simpler formula. And the same for Wishart matrices.
My question was, what motivated? It's not a fair question.
No, it is because we had this formula at first order. We had these second order cumulants. So then the question is, can you find the, yeah, this formula doesn't have a name, but I'm going to propose we call it the Voiculescu relation, because that's what he had in his first paper. And I think it needs a name now, 40 years out. And so I think call it the Voiculescu. I've been calling it in a couple of papers, the Voiculescu relation. Yeah, but here's a couple of other things. Yeah, to get down to here, I forgot, you have to differentiate that relation, because there's some things that appear when you differentiate. And the same when you do, no one's defined infinitesimal freeness, but there's a relation between, there's an infinitesimal Cauchy transform and an infinitesimal R transform, which you can get. And again, you have to, in order to simplify the relation, it's quite simple formula, but you have to differentiate the Voiculescu relation to kills a whole bunch of terms. So initially you get some big expression, which looks horrible, but then a big chunk of it is zero because it's a difference of the derivative of the left-hand side and the derivative of the right-hand side. And when you go to second order, you get the second derivative. And when you keep differentiating this thing, and this is actually just the derivative of the composition of two functions. Right? It's the K transform and the G transform. And that's higher derivatives are given by this Fad-de-Bruijn formula or something. Wasn't that? I forgot what. There's a theorem in combinatorics about how to compute a high derivative of a composition of two functions just by complicated applications of the chain rule. And I think, yeah, you can parameterize it using another thing that's kind of Boolean stuff. So Boolean independence somehow makes an appearance. Okay, sorry, let's put it up. And it is from, who's it? JC. Okay. So he says, okay, other than GUE. So he said, I think he's asking me what happens if you take A plus UB U star. So yeah, let me see. If you, yeah, let me just see. So if, I mean, so I think he's asking me if the second order cumulants of this thing are zero. No, he hasn't answered. But let's suppose that's the question.
I think he's asking about possible examples of GUE.
Yes. Yes, that's right. So
Yeah, U is hard unitary.
okay, yeah. So I mean, the R transform of the sum is the sum of the R transforms, and so now you're just asking about the second order R transform of A and B, and so if they're zero, then this is true. Yeah. So conjugating by a higher unitary makes them, and if these are independent, then that makes them free. So that's a theorem that Roland and Piotr Schneidy and I proved before we had the cumulants. And yeah, so here's something I never mentioned. So initially, we had a moment formulation of freeness. So remember in the very beginning, my very first slide, I said an alternating product of centered elements is centered. And that was what Voiculescu gave as a definition of freeness. And later Roland showed that's equivalent to vanishing of mixed cumulants. So initially Roland and I came up with the definition for second order freeness entirely in terms of moments. It involves spoke diagrams. So something could be reduced to spoke diagrams. So a second order moment could be reduced to a first order moment only involving spoke diagrams. That was the simplification. And then so that was the definition of second order freeness. And then we proved that these two guys were second order free, but we had no cumulants. We just had our definition. Then we found the cumulants. And so then you could just say vanishing of mixed cumulants, but initially we had to do it using that definition of second order freeness involving only moments because there were no cumulants. Now, there was a question too before.
Actually, I think maybe you already answered any like a relation for non-second order.
Is any random matrix model what?
Second order.
Yeah, so there's any, I mean, so okay, there's two things here. I mean, you need a second order distribution. That means you have all those moments, right? Just like in infinitesimal freeness, you have to assume that you have a limit.
Or we can
Yeah, but, okay, but I mean, let me go back. So first you have to assume you have two random matrices that have limiting distributions. Otherwise, there's nothing to talk about. Okay, but many examples do. And then the question is, would they satisfy the rule for second order freeness? And there's a theorem that says, if you're unitarily invariant and independent, then they are. Or there's even a more general theorem that if you conjugate by an independent Haar unitary, that will produce second order freeness. And then Emily Redelmeyer, who's going to talk on Friday, looked at real second order freeness. And then there's also a similar theorem when you conjugate by an orthogonal matrix. And you get real second order freeness by doing that. That's another discussion. Yeah,
So I think,
it's time to stop. Yeah.
yeah, let's
Uh-huh.
thank Jamie again.
Yeah, okay, yeah.